Hello students, today we will study about dipole. So what is a dipole? If we have a pair of equal and opposite charges and these are kept at some distance, then we call this pair as a dipole. So what we have? We are having two opposite charges as plus q and minus q, and these are kept at a distance of 2a. One is plus q and another is minus q, and the distance we are taking between them is 2a. So then this system of charges we call as dipole. So these are at a distance of 2a. We have just doubled the distance. So here I am drawing a dipole. Say this is a charge plus q and we have another charge minus q. And we have another charge minus q, and the distance between these 2 point charges is taken as, say this is the center of the dipole, and the total distance between these two charges is 2a. We have simply doubled the distance because whenever we are studying about dipole, we do any derivations or we do any type of numericals, then the center of dipole is very important. As you can see that here is the center. So whenever we want to calculate this, the distance from the center to any of the charge, then we can easily take this distance as small a. So the distance from center to any of the charges a, we need not half the distance. So initially we are taking it as 2a, and now we can easily write the distance from center to either plus q or minus q as a. So this is a total system of dipole where two charges are kept at a distance of 2a. So how we can define dipole? A pair of equal and opposite charge makes a dipole. So that is a very easy definition of dipole. What is a dipole? The pair of equal and opposite charges is called as dipole. Now come to the meaning of dipole. What is dipole? So di word itself means two. Di denotes two, and pole means the polarity. Here we are having two polarities. One is positive and the other is negative. So we have two types of polarities. So this is known as a dipole. Whenever we have two polarity, then we call it as a dipole. Now what is the physical meaning or the physical significance of the dipole? We know about the dipole, but what is the significance of this dipole? Let's go to the physical significance of dipole. So we have two types of molecules. First we can say are known as the non-polar molecules, and other type is the polar molecules. So what is a non-polar molecule and what is a polar molecules? In the non-polar molecules, the center of positive and negative charges are in the same place. So if we have a plus q charge and a minus q charge and their center lies at the same place, then we call it as a non-polar molecule. They do not have any polarity, and as a resultant, their dipole moment is 0. For all the non-polar molecules, charge plus Q and minus Q, the center lies at the same place, so their dipole moment is 0. And whenever any electric field is applied, initially it is 0, but whenever any external electric field is applied, then such molecules developed an electric dipole moment. Examples, as I have written, common example are carbon dioxide CO2 and methane CH4. Now come to the polar molecules. What happens in the polar molecules? The center of positive and negative charges. That means if we have two charges, plus Q and minus Q, the center of these two charges do not lie at the same place. That means the center do not coincide, and as a result, they have a permanent electric dipole moment. And remember, all the polar molecules, and the common example is water. So water, you can remember, always is a polar molecule. That is the first thing that comes to the polar molecule. So you can take water or H2O as an example of polar molecule, and they have a permanent dipole moment even in the absence of external electric field. If there is no electric field applied, then there exists a dipole moment because these molecules have within themselves a permanent dipole moment. So you will remember non-polar molecules does not have a dipole moment, but whenever they are kept in external electric field, they get a dipole moment. Common example are CO2 and CH4, and the polar molecules, they already have a permanent dipole moment, and irrespective of the external applied electric field. Fine. And the example we can take it as water. H2O is the common example of polar molecule. Field of an electric dipole and dipole moment. So here we have shown a dipole. We have a charge plus Q and a charge minus Q, and these are kept at a distance of 2a. This is the center. So the distance of each charge from the center is a, as we can see, and we take a point P, which is somewhere at the axis of this dipole. So there are two charges plus Q and minus Q, and the distance between them is 2a. We have double the distance, so we can easily make it half, because the center of the dipole and the distance of this minus Q is a, and the distance of plus Q is a, and we want to calculate electric field somewhere here at the axis of the dipole at point P. So we will consider two cases here. In first case, we will calculate the electric field E at a point on the axis of dipole. So our dipole axis, as you can see, this dipole axis is plus Q minus Q, and this is the direction of our dipole axis. And here we have taken a point P, which is in the same direction as of the dipole axis. So we want to calculate the electric field at this point P. Right? And this point P is at a distance small r from the center. You can see this is a center and this is the point P. So the distance from the center to point P is given by small r. And second case, we will calculate the electric field due to this dipole at a equatorial plane. And now what is this equatorial plane? Equatorial plane is that plane which passes from the center of the dipole and is perpendicular to it. Okay, so if there is any field which is passing from the center and which is perpendicular to this dipole axis is called the equatorial plane. So we will first go to the electric field E at a point on the dipole axis. So let's go to that. So how would we do? We will calculate the electric field E at a point P, and this P is at a distance of small r from the center of dipole. So as we can see that this electric field E, due to the charge minus Q, we can easily write the electric field due to charge minus Q may be written as E minus Q is equal to, since the charge is minus Q, so we'll write down this is equal to minus Q upon 4 pi epsilon naught. Now this is the distance from charge minus Q to the center. Okay. So you can see the charge minus Q from the center is A, and then we have to move up to the point P because we are calculating at P. So the distance of point P from charge minus Q is up to the center A plus from center to P. So this is R plus A. We have written it R plus A, and since this is the square of the distance, so this is R plus A whole square, and the direction will be P cap. This is the direction of dipole. And the direction of dipole is always from minus Q to plus Q, and P cap is a unit vector which directs from minus Q to plus Q. So this gives us the expression for electric field at point P due to charge minus Q. Similarly, we can write down the electric field at point P due to charge plus Q. So this is equal to Q upon 4 pi epsilon naught. Then the distance of this charge plus Q to P. Fine. So as we can see, the distance from center to point P is R, and the distance from center to charge plus Q is small a. So if we subtract A from R, we will have the distance between plus Q and P. So we got this distance as R minus A. So we can write down here R minus A and the square of the distance. And the direction will be same. It will be P cap again. Here P cap is a unit vector. It directs from minus Q to plus Q. So this is the electric field due to minus Q, and this is the expression for electric field due to plus Q. So now we can calculate the total electric field. So the total electric field at point P due to this dipole. So the total electric field at P is equal to, it is written as simply capital E, and that will be the sum of electric field due to charge minus Q and electric field due to charge plus Q. So we simply add them up. So we put the values, the total electric. So the total electric field E may be written as Q upon 4 pi epsilon naught is taken as common. Then we have 1 upon R minus A whole square minus 1 upon R plus A whole square within the bracket. So this may be written as, this is equal to the total electric field is equal to Q upon 4 pi epsilon naught, and R minus A and R plus A we can take as R square minus A square, and since there is a square on these two terms, so we can write it as a whole square. So 1 upon R square minus A square whole square, and from here we have R plus A square minus R minus A square. Right? So if we want to solve this, we can again write it as Q upon 4 pi epsilon naught, and if we open this using A square plus B square is equal to 2AB, we have r squared plus a squared plus 2ar minus, now with a negative sign, we have a minus b whole square, so it will be minus r squared minus a squared, and minus minus makes a plus, so plus 2ar. And in the as LCM we have r squared plus r squared minus a squared whole square. So this is our LCM. And electric field, so this is inside the bracket. Now the electric field E may be written as, now see which terms cancels out. This r squared cancels out with r squared, a squared cancels out with a squared, and we have 2ar plus 2ar, that makes a 4ar. So E is equal to Q upon 4 pi epsilon naught 4ar upon r squared minus a squared whole square. So this is the final term we are having here. This may again be written as, the direction will be p cap, obviously, unit vector in the direction from minus q to plus q. Now we can impose a condition of this total electric field. Now what is the condition? That if we take the distance of point P, the distance is small r, the distance of point P from the center is small r. So we take this distance small r is very greater than the distance A. The distance of point P is very greater than the distance to the each individual charge. Then r has a very large value than A. So we can neglect the term A in that term. See, here you can see that we can neglect this A in terms of r. So because r is very large, so we can write down q upon 4 pi epsilon 4ar upon r square to the power a square. A is neglected, so we are left only with r. So this is r to the power 4, and the direction is p cap. Now see, this r cancels down with this r to the power 4, so we are left with r to the power 3 only. So again, E is equal to Q upon 4 pi epsilon naught r cube and 4a. So we have the electric field E as E is equal to 4qa upon 4 pi epsilon naught r cube, and the direction is p cap. So this is the final expression we are getting the electric field at a point P at a distance small r, which is on the axis of the dipole. Right? We have to remember these terms because once we learn the dipole moment, we will again write down this in terms of dipole moment. Right? So the final term is E is equal to 4qa upon 4 pi epsilon naught r cube, and the direction is p cap. Now we can move to our second condition, that is when the point P is situated at the equatorial plane. So let's move on to the second point. So here we have shown two charges, plus q and minus q, and the distance between them is a for each, and this is the center we have shown. So from center plus q is at plus a and minus q is at plus a, and this is an equatorial plane. We have shown the equatorial plane in a blue color, and we have taken any point P on this equatorial plane which is at a distance small r. So from the center to the point P, the distance is small r. Okay, and this is a point P, and we have taken this angle to be theta, and this distance is r, and the distance from center to plus q is a. So we can write down the distance between point P to q is under root r square plus a square. So let us move to the electric field. So the electric field due to plus q is 1 q upon 4 pi epsilon naught 1 upon r square plus a square p cap. How come r square plus a square? Because as you can see, if we make this triangle, this is point plus q, this is point P, and if we write down this point as point O, if we write this down as O, then from the triangle QPO, we can see that since this distance is r and this distance is small a, So this will be under root of r square plus a square. This is a 90-degree angle, so this will be under root of r square plus a square. So if we do the square, then we have the distance is 1 upon r square plus a square, and the direction is p cap. So this is the electric field due to the charge plus q. Similarly, we can write down the electric field due to charge minus q. E minus q is equal to q upon 4 pi epsilon naught, and again this is a charge minus q, so we can write here minus q, and the distance will be same. Now the triangle will be OP minus q. From this triangle OP minus q, the distance between minus q and p will be the same, under root of r square plus a square. So if we do the square, same 1 upon r square plus a square, and the direction is again p cap. So now we have the electric field due to plus q and electric field due to minus q. So we can write down the total electric field. So the total electric field E will be the sum of these two electric fields at a point P. So the total electric field at point P may be written as, if you can see that the electric field due to plus q is along this direction. Okay, it is along this direction. This is shown as e to the power plus q. It is going from point P, then in the upward direction e to the power plus q. And if you see, the electric field is in the same direction from q to P, and due to minus q, it is along the direction of minus q. From P, it goes towards the direction of charge minus q. So this is E plus q and this is E minus q. And so we have to take the components for these two, right? So here we can write down the components of these two. We can take the normal component as well as the horizontal component of these two charges. Now here you can see that if this is the charge plus q, then this will be the normal component of e to the power plus q, and this will be the normal component due to e to the power minus q. So these two are equal and opposite to each other. The normal component due to plus q and minus q are exactly opposite to each other, so they cancel out. Okay, equal in magnitude, opposite direction, so they cancel out. So we can write down that the normal component of the electric field E gives us the value of electric field as 0, because both cancels out. Now if we come to the horizontal component of these two electric fields due to plus q and due to minus q, then horizontal component we can calculate it. If we go to the diagrams, and you can see that if you take the horizontal component, then e to the power plus q will give you the component in this direction, d to the power plus q cos theta. Since this is a horizontal component, this angle will be theta, so this gives us e to the power plus q cos theta. And due to minus q, if you calculate, this will be e to the power minus q cos, this is 90 minus theta, so this will be e to the power minus q cos theta. So this is the horizontal component for both the charges, electric field. We can get the horizontal component, so the total electric field will be e to the power plus q cos theta in addition with e to the power minus q cos theta. And as you can see that for the plus q theta, the direction is in the direction of minus p, because p directs from minus q to plus q, and here the p directs here to here, and this is the direction of p, as you can see. So our e to the power plus q cos theta is in the opposite direction. Fine. So here we have taken the direction as minus p cap. Fine. These two are opposite, so we will write down here minus p cap. And similarly, we can write down for e to the power minus q cos theta. Fine. So this is again minus p cap. So the electric field may be written as, we take minus as common from both the terms. So this is e to the power plus q cos theta and then plus e to the power minus q cos theta is again we can take as a common. And now if we want to calculate the value of this cos theta, because minus we have taken common, so p cap is left outside. So the electric field E is equal to e to the power plus q has the value q upon 4 pi epsilon naught r square plus a square and plus e to the power minus q has the value of q upon 4 pi epsilon naught r square plus a square to the whole square. These two terms are added, so plus e to the power plus q plus e to the power minus q cos theta p cap. Now if we want to calculate the value of cos theta, we have to go back to see the diagram. So if you see the diagram here, then cos theta is equal to, so the total electric field E is equal to q upon 4 pi epsilon naught r square plus a square whole square minus taken as common and two q. If you add these q plus q, we will have 2q and the direction is p cap and with cos theta. Now we need to calculate the value of this cos theta. So if we see the diagram once again, let's see. Okay, so here we want to calculate the value of this theta. So cos theta will be equal to, here this distance is r, this distance is a, and this is the root of r square plus a square. So we can write down cos theta as cos theta is equal to, because this is theta and this line goes like this and then we are going to draw a parallel line. So that angle being an adjacent angle, this will again be theta. So both the angles are theta as you can see in the diagram. So cos theta simply is the base is a divided with hypotenuse, that is under root of r square plus a square. So this will be the value of our cos theta. Cos theta is equal to a upon under root r square plus a square. So this value of cos theta we will substitute in our expression. This is the expression. So simply we put the value of cos theta. So E is equal to, minus is common, 2q upon 4 pi epsilon naught r square plus a square and put the value of cos theta. So this cos theta will be equal to a upon under root of r square plus a square and p cap is the direction. So E is equal to minus 2qa and upon 4 pi epsilon naught, and if you see here r square plus a square has to the power 1 and here r square plus a square has to the power 2. So 1/2 makes it 3/2. So we can write it down as r square plus a square to the power 3/2 and the direction is p cap. P cap is equal to from minus q to plus q. So this is our expression for the electric field due to an equatorial plane. This is our final expressions, and once we know the dipole moment, then we can write down this expression once more. Now we again impose the same condition, that if the distance of point P from the center, that is small r, this small r is very greater than a, then in this term we can neglect a in terms of r. So the total electric field E may be written as E is equal to minus 2qa upon 4 pi epsilon naught r square to the power 3/2. So 2 cancels out. So this is 4 pi epsilon naught r cube and the direction is p cap. So in this condition, when r has a very large value in comparison to a, our expression for total electric field comes out to be minus 2qa upon 4 pi epsilon naught r cube and the direction is p cap. So here we have derived the expressions for electric field in both the cases on the axis of the dipole as well as on the equatorial plane. So from these two expressions, we conclude that our electric field depends on the product Q into A. In the earlier expression, we are having E in terms of Q into A, and here in this expression written above, we can see that the E depends on Q into A. Now we move on to our next topic. We will study about dipole moment. Dipole moment is represented with the symbol capital P. So whenever we are having a dipole, then we can represent its dipole moment with P, and P is equal to charge multiplied with the distance between those charges. So if we have a system of two charges, then we call it a dipole, equal and opposite charges, and if we multiply the charge with the distance between two charges, then we get the dipole moment. So here we can see the charge is Q and the distance between two charges may be taken as 2A. So then 2QA will give us the dipole moment that is represented with the symbol capital P, and it is a vector quantity. So we can say that the dipole moment P is equal to 2QA, and the direction is always P cap. P cap is the unit vector in the direction of minus Q to plus Q. So P cap is written as that this is from minus Q to plus Q. So whenever you draw a dipole, then always remember that PQ directs from minus Q to plus Q. Either you are doing a derivation or any numerical problem where you are choosing the direction, or all of your competitive exams, this is a thumb rule that P cap is always from minus Q to plus Q. So we have just derived electric field due to the dipole. At the dipole axis, we got the expression E is equal to 4QA upon 4 pi epsilon naught R cube and P cap. So here we have the expression QA. So we can write down this equation or this expression for electric field in terms of the dipole moment P. Since P is equal to 2QA, so that implies our electric field will now be equal to 2P. P is the dipole moment. So 2QA we have replaced with P. So we are left with 2P upon 4 pi epsilon naught R cube, and the direction is P cap. So this is the electric field along the axis of the dipole, and we have written it in terms of the dipole moment. Here P is the dipole moment. So whenever it is asked to write down the electric field in terms of dipole moment for a dipole, you can use a similar expression. Simply replace this with 2QA with the dipole moment P. And the direction of dipole moment is also in the direction of P cap. Fine. So for the second case, when we are using an equatorial plane, point P is situated at the equatorial plane, then we got the expression E is equal to minus 2QA upon 4 pi epsilon naught R cube, and the direction was P cap. So in this expression also, we can replace this 2QA with the dipole moment P. So it comes out to be minus P upon 4 pi epsilon naught R cube, and the direction is P cap. So this is again the electric field at the equatorial plane of a dipole in terms of the dipole moment P. And here we have imposed the condition when R was very greater than A. The distance of the point P was very large in comparison to the distance of the charge from the center. So R is very larger than A. So in this case, these are the two expressions. So what we conclude from these two? First point, we conclude that here E does not follow the inverse square law. The electric field is inversely proportional to the cube of the distance R. So whenever there is a dipole, the electric field varies with the inverse of cube of the distance. Second point, E depends on theta. E depends on the angle theta also. Whatever is the angle then that decides the value of E, as you could see in the second case where we took the components. So it depends on the value of cos theta and sin theta. So E depends on theta. Third point is that if our two charges of the dipole, if the dipole are at zero distance, that means our charge plus Q and minus Q are at the same point, then we can call them as the point charge, and the dipole moment P is equal to Q into 2A. The distance becomes 0, the charge becomes the point charge, and the value of P is finite. Our dipole moment is finite, and we call it a point dipole. Now we'll take our electric dipole in an external electric field, which is a uniform electric field E. Our field is uniform, that means the electric field E is same everywhere. So this is minus Q charge and this is plus Q charge, and both the charges are kept at a distance of 2A from center. Each charge has distance A. This is A and this is again A, and this we have shown the center of the dipole, and here this P cap is along minus Q to plus Q. That also shows the direction of dipole moment P, because P is along in the same direction as the dipole axis. So our P cap is along minus Q to plus Q, and our dipole moment P is also in the same direction, minus Q to plus Q. Fine. So we want to say this angle is theta. Theta is the angle between this P, and now we want to calculate P and E. Electric field and dipole moment are at an angle theta. So we can write down the dipole moment P as Q multiplied with 2A. So that gives us the dipole moment. This is equal to 2QA. So now we want to write down the force on charge plus Q. Because our dipole moment is an external electric field, so it will experience some force due to the electric field. So the force on charge plus Q is QE, because this is plus Q. So F is equal to plus Q into E, and the force will be in the direction along the electric field. Similarly, the force on charge minus Q will be minus Q multiplied with E. Then this will be opposite to in the direction of electric field. Fine, because charge has no direction, so their direction are opposite. So if we calculate the net force on the dipole, this is plus QE minus QE. Both are equal and both are in the opposite direction, so the net force comes out to be 0. Why the net force is 0? Because our electric field is uniform everywhere. Mind this thing. Electric field is uniform, it is same everywhere, so plus QE and minus QE cancels each other, and the net force comes out to be 0. Now there is an equal and opposite force. So whenever there is an equal and opposite force, then the torque comes into picture. So there will be a torque on this dipole which is acting on the dipole. Force due to charge plus Q is plus QE, force due to charge minus Q is minus QE, and these two are equal and opposite in direction. So there will be a torque which is acting on this dipole, and this torque we can write this torque as tau. So we can say that there exists a torque which is given by tau, and tau, this is the symbol for the torque, we call it tau, TAU. This is our symbol tau, and this is, we pronounce it as TAU, tau. So tau will be acting on our, so this tau is equal to F cross D, where F is a force, which is two forces equal and opposite, the magnitude of that force, and D is the distance. So in our case, the force which is acting on each charge is QE, equal and opposite, and the distance is 2A. So this is QE cross 2A. So the torque tau may be written as QE, and the cross product will give us sine theta. Here theta is the angle between this E and our dipole moment P. So this is QE 2A sine theta, which may again be written as QE 2QEA sine theta. Now in this torque tau we can represent, okay, here we can see that in the diagram this is the angle theta which is between the P, the dipole moment P, and the electric field E. The dipole moment P directs from minus Q to plus Q, and E is in the perpendicular direction. You can see, or if it is in any direction, then we can take the angle theta. So tau may be written as 2Q as 2QA. We can replace with P. So this is PE sine theta. And if this is P sine theta, then we can simply write tau as P cross E, because cross products always gives us sine theta. So the simple expressions comes out for the torque tau is equal to P cross E. Since tau is a vector quantity, P is also a vector quantity, dipole moment, electric field. So tau is equal to P cross E. So there is a torque which is working to align our dipole along the direction of electric field. What is the work of this torque? This torque is continuously working on the dipole to make it align along the direction of electric field. So our dipole will rotate till it aligns in the direction of E. Right? So that is the work torque is doing, and when this torque will align our dipole moment completely in the direction of electric field E, then what will happen? Then our torque tau will stop working. So torque tau will stop working when the dipole moment P and the electric field E are aligned in the same direction. So when these two are in the same direction, then our torque tau will become 0. So tau will have the value of 0. And in that case, our dipole moment P and the electric field E will be exactly parallel to each other. Parallel will make the theta as 0, and sine 0 will have the value of 0. So our tau will become 0. So the tau is equal to P cross E, which may be again written as PE sine theta. And when P and E are parallel, theta will have the value of 0. The angle between them is 0, and sine 0 makes a 0. So tau will completely become 0. There is no torque acting on the dipole. So we have proved that this tau is equal to 0 from our result, from the formula, and as well as we can see here from this formula we can see P equal to P cross E is equal to 0. So when these are aligned, tau will work till they are aligned. So theoretically tau will become 0, and according to a formula, when theta will become 0, then tau will become 0. Say this is our dipole which has a minus q and plus q, and p cap shows the direction of the dipole moment. Then this is the direction of our dipole moment. This is p cap. Okay. So when this completely aligned in the direction of electric field, then tau will stop working. So when P is parallel to E, when P and E are in the same direction, then there is no torque working. Now second, we are considering when our dipole is placed in a non-uniform electric field. This is the electric field with vector E, which is not uniform. Means E is not same everywhere. At every point E may vary. That means we have a varying electric field, or which is a non-uniform electric field. So let us see how our electric dipole will behave. Since E is not 0 at each point, so our total force, net force, will not be equal to 0. But it will experience a torque. So there is always a torque which is present. Net force is not zero, that means force is present, as well as the torque, tau is present for a non-uniform field. Why there is a net force? Because E is not same everywhere, so plus QE and minus QE doesn't cancel out. And when there are two forces which are acting in the opposite direction, there will be torque. So we can take two cases. First case, when our E is parallel to P, that means our electric field E and the dipole moment P are parallel to each other. That means the distance, the angle between them is 0. And in the second case, I am writing as this, E is anti-parallel. Okay, this simply denotes that E is anti-parallel to P. So parallel, I have drawn a line. So it only shows that E and P are anti-parallel to each other. The angle between E and P is 180 degrees. So let's go one by one. So first we consider the case when E is exactly parallel to P, when our electric field is in the same direction as our dipole moment. So say this is our first charge represented by minus Q, this is our second charge plus Q, both at a distance of 2a, and this is the direction of P cap. Here is the center, and from minus Q to plus Q is the direction of P cap that shows the dipole axis, or that also shows the direction of dipole moment, and the E is also along the same direction. So E and P are parallel, as you can see from this diagram I have drawn. So E and P are exactly parallel to each other. So if we calculate the force on charge plus Q, that is plus QE, and similarly if we calculate, this is around this direction, see FQ will be in the same direction of E because Q doesn't have any direction. So F plus Q is in the direction of plus E, and F minus Q will have the magnitude of minus QE, and the direction will be in the opposite to E because this is minus E. So the force on charge minus Q will be in the opposite direction to that of the electric field as I have drawn. So this shows the force on the charge minus Q. So as you can see that F plus Q and F1 minus Q are opposite, but they may not be the same because electric field is not same, not uniform. So this is how we can show the two forces which are acting in the opposite direction but are not same. Now we calculate the net force which is acting on this dipole. So the net force will be acting along the plus QE, as you can see, and here in this direction the electric field is increasing. So net force will be is in the direction of increasing electric field. So this is plus QE and minus QE. So wherever the electric field is increasing, the electric field is large, the net force will be acting in the same direction where our electric field is increasing. So what we conclude that when E and P are in the same direction, they are parallel, then the net force is acting in the direction of increasing electric field. Right? So this shows the net force, and if we go to our second part is when E and P are anti-parallel to each other. They are in the exactly opposite direction. Say this is our charge minus Q, this is our charge plus Q, here is the center, and this shows the direction of dipole moment, that is from minus Q to plus Q around the unit vector P cap. It is also in the direction minus Q to plus Q, and this shows the direction of electric field. Now in this case you can see that electric field is in the exactly opposite direction to our dipole moment. So we can say that these two are anti-parallel. Electric field is in the opposite direction to our dipole moment. So we are calling them anti-parallel, or the angle between them is 180 degree. Now quickly calculate the force on each of the charge. So the force on charge plus Q will be plus QE, and similarly the charge on minus Q will be minus QE. Let's write down the expression, and then the net force will be in the direction of decreasing electric field, because here is the direction of dipole moment and this is the direction of electric field. So if you write down plus QE and minus QE, then the resultant will be in the direction of minus E, means the decreasing direction of the electric field. So when E and P are anti-parallel, are exactly in the opposite direction, then we can conclude that the resultant force will be acting in the direction of decreasing electric field. Hope it is clear to you, and this dipole and dipole moment are expressed in a very simple way to understand, and this may help you. And if you find our lecture interesting, you can move on to, you can like and share, and you can subscribe to our channel and keep on watching for many such videos on easily understanding physics. Thank you. Keep on watching, like and share, and subscribe our channel. Thank you so much.